in this lesson, we're going to discuss inverse trigonometric functions, and in particular, how to take the derivative, differentiation of inverse trig functions. This is going to be fairly lengthy notes, so let's jump right in. We have three objectives: develop the properties of the six trig functions, so basic properties. We'll start out with a little bit of review. Differentiate an inverse trig function. In particular, we will prove the derivative of inverse sine and inverse tangent. And then finally, at the very end, I'll ask you to pause the video and focus on the table on the last page of these notes, which is a review and summary of basic differentiation rules for what we call elementary functions. All right, so jumping right in, the definition of an inverse trig function. You learned about this first in your pre-cal class. I don't believe you would have seen it in your Algebra 2 class, but essentially your inverse trig functions are functions that are created from restricted domains on our original basic trig functions. So what I mean by that, if you look at the graph down here, if you take the sine graph, which is what this is, all right, just the basic sine graph, and you restrict its domain from negative pi over 2 to positive pi over 2, and take just that curve highlighted here in the darker black, that curve has properties that solve or work for what we call the horizontal line test, meaning I could draw any horizontal line through that black curve and it will never intersect the black curve more than once. We've discussed this horizontal line test in the past very briefly, but this is our formal discussion as it pertains to inverse trig, not just inverse functions of any kind. So if I don't restrict the sine curve to just that region between negative pi over 2 and positive pi over 2, if I leave it for the whole domain of sine, then the sine curve fails the horizontal line test, which is why I must restrict it. Because if I restrict it, then the inverse of that restricted curve, inverse of this, what we call inverse sine, will have a function as opposed to just another relation. All right, so we refer to generally the inverse sine curve, of course, as inverse sine of x using this notation, but many of you also know it as arc sine. All right, this arc sine is simultaneous. It means the same thing as inverse sine. It's just a different notation. You should not be confused by that. That's listed over here in the remark. The term arc sine is read arc sine of x. So just know that it means the same thing, and the AP exam does use both notations, so you got to know both. All right, and we've got listed, of course, arc cosine, arc tan, arc cotan, arc secant, arc cosecant. Now, I will tell you, the AP exam in particular focuses its attention primarily on inverse sine and inverse tan. Every now and then, the inverse cosine will show up, but I got to be honest, I have never seen an inverse cotan, inverse secant, or inverse cosecant differentiation problem. I have seen them in basic trig review problems here and there, but they're always multiple choice. Since your exam is going to be of a different format this year, I'm not so sure it's necessary to go full tilt into understanding and learning those unless you're just highly interested in it. All right, moving on. The keys, again, to the inverse trig functions are that you always remember the restricted domains. In order to get this inverse sine, we have to take inverse sine. We have to take the original sine and restrict its domain to negative pi over 2 to positive pi over 2, which means you are limiting the range, the output of inverse sine, because domain and range would swap. Notice the domain, the restricted domain here of the sine curve and the range, negative 1 to 1, have swapped with the domain and range of the inverse sine. All right, and the same follows with inverse cosine, which has to be which takes the cosine curve and restricts it to 0 to pi. I'm not sure I have regular cosine. I'll scroll back up here in a moment. No, I do not. So the regular cosine curve I'll just sketch very briefly over here. Regular cosine would graph in this manner, or something like that. And of course, here is pi, and so if I restrict the domain from 0 to pi, that highlighted portion will pass the vertical line, or sorry, the horizontal line test. And then, of course, inverse tan, if I take the tan curve and I just focus on the interval from negative pi over 2 to positive pi over 2, that function, all right, this is tan, while this one was cosine. All right, if I restrict the basic cosine curve from 0 to pi, if I restrict the tangent curve from negative pi over 2 to positive pi over 2, then I get an inverse function when I swap domain and range, when I switch x's and y's. All right. One last statement here about this table. Hopefully you've got it copied down into your notes by now, but notice the statement here says y equals inverse sine if and only if sine of y equals x. Well, that makes sense because if we start with, for instance, in the sine curve, if we start with y equals sine, the original sine curve, and then we swap out the x and the y, as soon as we switch x and y in any function, we have created an inverse. All right, now, if we do that here, we get sine of y equals x, which is what's written here. But the truth is, we generally don't leave any function written in this way. We want our functions solved for y. So to solve this, to get that y extracted, we do inverse. We write it in this fashion, or arc. All right, enough of that. The graphs, I'm not going to focus on these graphs too much because the AP exam doesn't focus on it. It's not necessary. But the graphs of the inverse functions would look like this. You can copy these down real quick if you'd like, but again, it's not all that important. If this was a BC class, it might be a little bit more critical for us. But here, not all that important. Just to look at what these arc sine or inverse sine graph looks like this, inverse cosine looks like this. Pay attention, of course, to the switched domain and range. By switched, I mean swapped from the original sine and the original cosine and the original tangent and so on. All right. Also notice one characteristic here of tangent, and that is that the domain becomes infinite. Since the range of regular tan was infinite, the domain of the inverse tan becomes infinite. They switch. All right. So you can pause the video and take a look at those graphs and write them into your notes if you'd like. But I am going to move on into some pre-cal review. All right, so let's practice a little bit of evaluating inverse trig functions. In this first example, it just says to evaluate. So in part A, if we know that arc sine of negative 1/2 is some value, well, we don't know what that value is, then we'll rewrite it, setting it equal to an unknown. And instead of arc, I prefer to write, if I'm writing it, I'm going to write inverse sine in this way instead of arc sine. So I don't know what it equals, so I'll just say it equals x. It equals some value x. All right, so if inverse sine of negative 1/2 equals x, well then that means that the original sine of x must equal negative 1/2. And then we're just basically asking the question, what value do we need to plug into sine? What does x need to be to plug into sine in order to get negative 1/2? This is where your unit circle review might be helpful. Hopefully you haven't forgotten all your unit circle information. But of course, sine will equal negative 1/2 somewhere in quadrant 3 or 4, right? Negative 1/2, over here for sine, that's the y value, or over here, right? But then we have to draw on the fact that we were originally discussing an inverse function. So we can only use values, sine can only yield values in specific range. So that range does not include quadrant 3. Sine needs to be a value between negative pi over 2, and positive pi over 2. All right, negative pi over 2 and positive pi over 2 is what I've highlighted here in the blue, which means it must be this value. And that value, if you go from the positive x-axis down, is negative pi over 6. So our answer here, x must be negative pi over 6. All right, again, when we're dealing with inverse trig functions, we have to remember which domain values are which range values are possible. Or you could say which domain values in the original sign are possible. All right, moving on, B. So same idea here. If arc cosine of 0 is what we're calculating, then I'm going to say inverse cosine of 0 equals some value, I'll call this value x, which means cosine of x must equal 0. And it's a simple question. When does cosine equal 0? Well, remember, cosine does equal 0 in two places. It equals 0 both, whoop, that was my door locking automatically. It equals 0 both up here at pi over 2 and down here at negative pi over 2. Let me do these in a bolder color. Maybe it'll pop out a little bit better. At pi over 2, or you could say, most of you probably remembered it as 3 pi over 2. But our cosine function needs to be restricted to a domain of 0 to pi in order to even get inverse cosine, which means the inverse cosine has a range, the output, this value over here is on the other side of the equal sign, so it's the output of the inverse cosine, must have an output between 0 and pi. So therefore our x value must be pi over 2, which is between 0 and pi. All right, moving on, C. I'm going to start by saying inverse tan of root 3 equals x, which means tangent of x equals root 3. And we're asking ourselves, when does tangent equal square root 3? Well, if I go up to my unit circle up here, you may remember that tangent equals root 3 at the coordinate of pi over 3, and also all the way over here at 4 pi over 3. We can't use the 4 pi over 3 for the same domain restriction ideas or concept that we discussed with the previous two problems. So we're going to have to stick with the pi over 3 value, but you may be confused, why is it at pi over 3? All right, why is it this angle pi over 3? Oops, pi over 3, not pi over 2. Because the x-coordinate here would be a half, the y-coordinate would be square root 3 over 2, and since tangent equals y-coordinate divided by the x-coordinate, when you divide square root 3 over 2 by a half, you get square root 3. So x must be pi over 3. All right, one more in this group of questions. D, arc sine of 0.3. Well, this one's a little bit easier, only because the only way to calculate this one is on a calculator. So arc sine of 0.3 equals some unknown x, which means sine of x equals 0.3, but the simple fact is 0.3, 1/3 is not a memorized value on the unit circle. That was not one of the values you were ever asked to memorize. If it was 16 points on the unit circle you have to memorize, that's not one of them. So the only way to really calculate this value, since it's not directly related on the unit circle, is by using a calculator. Make sure your calculator is in radian mode. Again, always radian mode in the AP exam. Always radian mode. And if you calculate inverse sine of 0.3, you're going to find x is approximately 0.305. 0.305. There we go. All right. Again, all that's pre-cal review. No calculus yet. We haven't taken a derivative or an integral, so we haven't done any calculus. Let's move on. Inverse functions have certain properties. All inverse functions have the property that when you compose two inverses together, when you compose, I'm going to use a thicker highlighter here. When you compose, meaning you put one inside of the other, whether you put the inverse as the input of the original function, inverse inside the original, or you put the original inside the inverse. When you compose them, they simplify the x. Now, this is true so long as we remember the restrictions on the domain. For example, this here says arc sine of sine pi. Well, you might be tempted to just look at this problem and go, oh, well, the arc sine and the sine will cancel, and I'm just left with pi. Problem here is that the output, ultimately, the final answer is an output of the arc sine, right? It's arc sine that we are evaluating. It just so happens that we're evaluating it at sine pi. And sine must be a value, arc sine must yield a value between negative pi over 2 and, let me scoot over a little bit, and positive pi over 2. And pi just is not in that domain. All right? So is there another value that works in this function, or is there another value that inverse sine could yield? Well, yes, there most certainly is. And the best way to remember this is to say, let's work from the inside out. Sine of pi is a very easy value. Sine of pi is 0, right? So we're really evaluating inverse sine of 0. Or you could, let me just keep it simple. I'll leave this as arc sine, all right? We're evaluating arc sine of 0 because sine of pi is 0. And then arc sine of 0, there wouldn't be any confusion. You would go, okay, well, inverse sine of 0 equals x. So that means sine of x equals 0. And where does sine equal 0? Yes, at pi, but also at 0. And so you would realize, okay, well, the answer must be 0 because that's in our assigned domain. So you got to be careful with these. Don't just blindly cancel out because the answer must always fall within the restricted domain. All right. And so this table here, this chart shows the properties, the basic properties of the inverse trig functions. Sine of inverse sine of x usually yields x so long as our x is in the assigned domain. All right. And arc sine of inverse sine y equals y and so on. Same is true for the inverse tan. Same is true for inverse secant. All right. Let us roll on. Solving an equation with inverse trig functions. Again, still dealing with pre-cal knowledge right here, no calculus just yet. So example 2 here says arctan of 2x minus 3 equals pi over 4. All right, let me write this in a slightly simpler fashion here. Arctan 2x minus 3 equals pi over 4. And if that's the case, then if I swap my domain and range, if I switch these out, then I undo the inverse tan and I get back to tan. So tan of pi over 4 must equal 2x minus 3. So I will simply evaluate tan of tan of pi over 4. That's a value off the unit circle, value off, you could do it a unit circle or you could do it off of the tan graph. Either way. Pi over 4 is root 2 over 2, root 2 over 2 as our x and y coordinates. And when you divide the y over the x, you get 1, right? So tan of pi over 4 equals 1, which means we have 1 equals 2x minus 3. And this equation is very, very basic. You end up just finding that x equals 2 when you solve for x, all right? Boom. Pretty simple equation there. All right, let's keep going. Using some right triangles. Now, I love these problems because they really do require you to get a little bit of thinking on here. They're not just so basic as the previous example, but they're more algebraic in nature, or they get you to think a little bit outside the box. I cheated some by giving you these triangles off to the side, but the fact is, when you're dealing with trig functions that you can't work out, remember all trig can be related to triangles. Trigonometry is essentially the study of triangles. That's what the word trigonometry means, the study of triangles. So when you can't figure out a trig problem, it's not a bad idea to simply draw a triangle and start outlining and writing out the information that's given. Lay it out on a triangle in some way. All right, so let's hop into example 1 here. Example 1 says, given y equals inverse sine, and remember that y, because it's inverse sine, y has to be a value. Oh, no, not remember, but they're actually restricting because we don't go to negative pi over 2. They're telling us that y has to be between 0 and pi over 2. And there's a reason for that. I won't go into too much detail about it, but essentially it's because they want you to use all positive values. If y is between 0 and pi over 2, then all the trig function values are positive because you're in quadrant 1. All right? So if we are told that y equals inverse sine, and then we're asked to find cosine of y. All right, well, if y equals inverse sine, right, if y equals inverse sine of x, then if I swap the x and the y, I get back to just plain sine, all right? Or I undo, in other words, the inverse property, the inverse function, and I'm going back to the straight sine function. So now they're telling us that sine of some angle y, that's a habit that you might want to get into, is to think about whatever is being plugged into a trig function is technically an angle. And that helps you to think about using a triangle. So if y is the angle plugged into sine, and it yields a value of x, then that means the opposite of angle y must have been x, and the hypotenuse must have been 1, because sine is opposite over hypotenuse. So if I place that information on a triangle, like you see off here to the right, angle y placed here, opposite side x, hypotenuse 1, then using the Pythagorean theorem on right triangle trig here, right, using the Pythagorean theorem, I find that the adjacent side, right, the adjacent side to my angle y must be square root of 1 minus x squared, right, Pythagorean theorem. So if I'm asked to calculate cosine of y, well, cosine of y is the adjacent side over the hypotenuse, which gives me square root 1 minus x squared over 1. Of course, I don't need to write it over 1. I could just write it as square root 1 minus x squared. So there's my answer. Done. It's not a value that I'm solving for. It's an algebraic expression, and we've got it. That's it. All right, so moving on. B. B says we are given that inverse secant, arc secant of square root 5 over 2 is equal to some value of y. All right, so if inverse, oops, I said inverse sine. I should have written inverse secant. If inverse secant or arc secant of root 5 over 2 equals y, well, that means that, I keep doing sine, I'm used to it here, and that means that secant of y must be root 5 over 2. And we recall that secant is hypotenuse over adjacent. All right, so if our angle is y, we put that on a triangle, and we say the hypotenuse of that triangle must be square root 5, the adjacent side must be 2, and using the Pythagorean theorem, you would find that the opposite side measurement must be 1. So if the opposite side is 1, then we can go answer the question they asked. Find tangent. So therefore tangent of y, same angle y, right, again, when in doubt, use a triangle, and that's what we've done here. All the information that we need is right here on this triangle. Tangent of y is, of course, the opposite, 1 over the adjacent, 2. And there's our answer. This one, because we had a value, as opposed to the previous one where we just had x, because we had a value here, we could actually solve for a number. All right, so there you go. Again, none of this is calculus yet. Now we start the calculus. Notice the heading on the next group of problems here, a large blank here so I can do some work. We're going to calculate and prove the derivative of inverse sine. All right, so to start out, we're going to say, let's let y be some function inverse sine. And if y is inverse sine, then remember if I swap the x and the y, I undo the inverse and I get back to sine. This is where we are going to focus our attention, here on this statement. Remember that we've got a domain restriction. We'll just keep that in mind as we work this problem. Meaning the y value in this has to be between negative pi over 2 and positive pi over 2, because that was the output of the inverse, right? Has to be a value in quadrant 1 or 2. I'm sorry, quadrant 1 or 4, I should say. All right, so if I focus my attention on this sine y, and then I differentiate implicitly. All right, implicit differentiation says take the derivative of sine is cosine, leaving the input alone, and then multiply by the derivative of the input. So the derivative of the input dy is dy dx. I'm multiplying by the derivative. We're differentiating here with respect to x. So cosine of y dy dx must equal, well, the derivative of x with respect to x is just 1. We know that. So if I solve for dy dx, then dy dx is simply 1 over cosine of y. All right. Well, if I go back just a hair, well, in the beginning, we stated that y was inverse sine of x. So really, this is 1 over cosine of inverse sine of x, all right? And there are a number of ways you could do this, to be honest with you, but the fact is we actually just said in the previous problem, if I scroll up a hair, that if y equals inverse sine, then cosine of y is square root 1 minus x squared, right? So if I go down right here, I already know, without even considering this stuff, if I just ignore the fact that I just replaced the y with this, without even considering this fraction here, I already know from the previous problem that we just did that cosine of y is square root 1 minus x squared. So the derivative of inverse sine, if I want it just in terms of x, the derivative of inverse sine is 1 over square root 1 minus x squared. But I want to go a little deeper into this and just say, if you happen to forget this, or if we had not done that example earlier just a moment ago that said cosine of y was this, then you can also do this using a little bit of creativity, right? We can handle this cosine in a slightly different fashion. So let's do this. If I were to say that, oops, I don't know what happened there. Here we go. If I were to say that, remember our Pythagorean identity, sine squared y plus cosine squared y equals 1, right? Then cosine squared y is equal to 1 minus sine squared y, right? And cosine of y is equal to square root 1 minus sine squared y, right? And we just said earlier that sine of y equals x, right? When we rewrote this original statement, swapping the x and the y, we got regular sine. So that means this is basically just x squared. So even if you had forgotten using the triangle from earlier, you could solve this using the Pythagorean identity, sine squared plus cosine squared equals 1. This is just another way to think about the same thing. And again, what we're doing is we're evaluating this whole piece. All right? All right, I think that's about enough of that. The official formal derivative for inverse sine is right here. Write it down, make sure it makes sense to you. Let's move on. All right. All 6 inverse trig function derivatives right here. Notice the next example, we are actually going to play with a little bit. I've got the derivative of inverse tan right after. We're gonna work this here or discuss this here in a moment. But the 6 trig derivatives. You can pause the screen, write these down. But before you do that, let me state straight up that you would not have to do all of these. To be honest with you, I have never seen I have never seen inverse secant on an AP exam. I have seen inverse cosine, but it's few and far between. I've never seen inverse cotan. I've never seen inverse cosecant. All right, so rather than cross them out, I'm just going to say it this way. The two that you should focus your attention on, the two that you absolutely need to know, is inverse sine, which we just talked about. Why that can't give me a nice, neat oval, I don't know. There we go. Inverse sine, and of course, inverse tan. That was a mess. I'll tell you what, let me do this one in a square. See if that works any better. Inverse sine and inverse tan. These are the two you need to know. You absolutely should memorize. Inverse sine we just talked about. Inverse tan I'm going to show you here in just a moment. All right. The rest of these, if they showed up as a question, they're definitely not going to show up as a free response question. I can tell you that. But if they showed up as a multiple choice, yeah, I would probably rewrite it in terms of another function. But I'm not going to hit those here in these notes for sure. All right, let's do one more pre-cal question here. If you needed to, again, pause the screen right here on these, write these down. But let's move on. Simplify the expression cosine of inverse tan. When you're composing two trig functions, especially if one of them is inverse, you need to remember domain restrictions. So we know that this has to be a value between negative pi over 2 and pi over 2. I'm sorry, between negative pi over 2 and positive pi over 2. Yeah, I said it right. But here's the problem. All I have is x, right? I'm given cosine of inverse tan of x. If I don't have any value here, I know my answer is going to be algebraic. I'm not going to get a result that is a number. It's going to be some sort of algebraic expression, all right? Because I don't have any numbers. Okay, so with that in mind, that kind of gives me an idea that I'm going to probably use a triangle. I'm going to probably use something to try to express this. I'm not going to be able to just pull this out of thin air. All right, so the way I like to think of it is I'm taking cosine of something. All right, and generally the input of a trig function is an angle. So I'm going to call tangent theta. Let's call all of this, or inverse tangent of x. I'm going to call all of this theta. All right, so inverse tangent of x is theta. And then what I'm really trying to calculate here is cosine of theta. All right, so if inverse tangent of x equals some theta, some angle that has been plugged into cosine, then that means tangent of theta equals x. All right? And if tan theta equals x, then on a right triangle, that didn't want to draw a right triangle for me, did it? That one did. That's okay. Then on a right triangle here, if I throw a theta in, choose theta to be some angle somewhere, then the opposite side must be x, the adjacent side must be 1, because tangent is equal to opposite over adjacent. Which leaves me with right triangle trig, which leads me with the hypotenuse must be square root of x squared plus 1. Or you could say 1 plus x squared. All right? So if the hypotenuse is square root x squared plus 1 or square root 1 plus x squared, again, Pythagorean theorem here used to find this, then cosine of that same angle theta must be adjacent over hypotenuse. All right? So that must be 1 over square root x squared plus 1. Or again, 1 plus x squared. All right. They're a very simple problem. There it is, done. The reason why we're doing this is because it's going to help us with the next problem. All right? So I want to evaluate inverse tan. Now, I've got this already printed and worked out here, so you're going to take a few moments and write it down. But our job here is to prove why the derivative of inverse tangent, why the derivative of inverse tangent is 1 over 1 plus x squared, as you see at the box at the bottom here. All right, let me walk through it with you very quickly. Because tangent is differentiable, all right, the regular tan is differentiable, then its inverse function must also be differentiable. To find the derivative, we're going to do this explain this similar to the way we did sine. We're going to start out with y equals inverse tan. We're going to rewrite it as regular tan by swapping the x and the y. We switch the positions of x and y. Then we're going to use implicit differentiation. All right. differentiating implicitly with respect to x. Okay, so the derivative of tangent is secant squared. Notice the y is still there, and then we have to multiply because it's implicit differentiation. We have to multiply by dy dx. And of course, the derivative of the right side, derivative of x, is 1. Okay? I've written this property over here. It's locked in because that's going to be important to consider and think about this. If I go further, dy dx, if I solve this for dy dx, that's my job. I wanted to find the derivative of inverse tan. I'm going to divide by secant squared. All right? And then, using Pythagorean identity, I remember that secant squared of any angle is equal to tangent squared of that angle plus 1. Again, this Pythagorean identity that you memorized in pre-calc. So I can rewrite this as 1 over 1 plus tan squared. Okay? Well, just like we did earlier on the inverse sine function, tan of y equals x. So tan squared of y equals x squared. All right, so very simply, the derivative of inverse tan is 1 over 1 plus x squared. Very simple, elegant proof, works out nicely. This one must be memorized, just like the inverse sine function. All right, let's roll on. Now that we have these, let's practice some derivatives. This is officially getting into some actual problems and practice problems with differentiation. So here we go. Derivative of inverse sine. It might be a good idea, by the way, since you've got these properties now written down, to take a moment, pause the video, and try these on your own. Try to evaluate each of these on your own, and then go back and watch the video and see if you got it right. All right, I'm going to move on. Let's practice. The derivative of inverse sine, or arc sine. Notice this input is not x. If the input isn't x, the input is some other function of x, then we're going to have to do the chain rule. We're going to have to deal with the chain rule. We have to multiply by the derivative of this input. So the derivative of inverse sine is 1 over square root 1 plus the input squared. All right? If you're scratching your head right now, remember we wrote the derivative of inverse sine of x is 1 over square root 1 plus x squared. I'm sorry, back up, 1 minus x squared. I'm just remembering. That would have been a massive, colossal error. Sorry about that. Common error, to be honest with you. So 1 minus x squared. All right. But we have x here, and in our problem we have 2x. So the input goes here. In other words, if this was a u, this would be u squared, and then we multiply by du dx. I think actually that was how I originally expressed. If I go back up, that's how it's expressed here, right? If it's u, if it's some function of x u, it's going to be u squared, and then we multiply by u prime, all right? So that's where we are in this problem. We have to multiply by the derivative of 2x, which of course everybody knows is just 2. So our answer is 2 over square root 1 minus 4x squared. Be careful when you square here. I see a lot of students that forget to square the 2, and they just square the x and call it 2x squared. This should be 4x squared. All right, moving on. Let me box that off. That was our answer here. The second one here says take the derivative of arctan. Well, we just did this one. It is 1 over 1 plus the input squared, and then we multiply by the derivative of the input, another factor of 3. And so our answer, if we simplify, is 3 over 1 plus 9x squared. All right, simple as that. Next one. Back to inverse sine, so it is 1 over the square root of 1 minus square root x squared, and then times the derivative of the square root of x. Derivative of the square root of x is 1/2 x to the negative 1/2. So we can clean that up a little bit. Notice that this x to the negative 1/2 is going to move into a denominator, and the 2 can also move into the denominator. So we have just 1 in the numerator, and I can write this as 2. To be honest with you, there are 2 ways to do this. I'm going to write it this way so it makes sense. Square root x times another square root 1 minus x. And where's that 1 minus x come from? Well, square root of x squared is x. All right, now if you really wanted to, you can go a step further and you can multiply, since these are both just plain square roots, you can multiply that x into, that square root of x into this, and maybe write 1 over 2 square root x minus x squared, if you felt so inclined, but you don't have to do that. All right. All right, moving on. D. I'm going to scroll up a little bit, give myself a little more room. Here we go. Now D has shifted gears here, and they've gone to the one that I said we wouldn't have to deal with much, which is inverse secant. It's one problem here. It may show up in your web assign, but like I said, it's not going to be on my math or in a free response question on an AP exam. It's just not going to show up. All right, but go back up to the formula. If you scrolled up to the formula, you would see that the derivative of inverse secant is 1 over absolute value of the input, which is e to the 2x, times square root of the input squared, e to the 2x squared, minus 1. And then, of course, because the input is not just plain x, but e to the 2x, we have to multiply by the derivative of e to the 2x. And derivative of e to the 2x is e to the 2x times 2. So 2e to the 2x. All right? And then here, notice e to the 2x is always positive already. All right? The absolute value is part of the formula, but e to the 2x is already always positive, so we don't need the absolute value here. And with that in mind, then the e to the 2x on the top will cancel the e to the 2x on the bottom, and we are left with 2 over square root e to the 4x. When you raise a power to a power, you multiply, minus 1. And that's our final answer here. Oop, I forgot to box off the previous one. Okay, hopefully that all made sense. Let's do a couple more. Number 5, differentiate y equals 1 over inverse sine, and then b x times inverse tan square root x. A lot going on. These are basically just a little bit more difficult because the first one is a chain rule, right? If I look at this closely, y is inverse sine of x, I forgot my negative 1 there, inverse sine of x to the negative 1 power. And the second one is written as f of x or y equals, well, you know what, I don't need to rewrite it. I'm sorry. I thought I was going to have to rewrite this, but I was distracted. Basically, it's a function x times inverse tan. We could rewrite it as yeah, I'll do that. I'll go equals x inverse tan square root x. How about that? Okay, so let's go back to A real quick. Derivative y prime is going to be the power times the function to 1 less power, and then times the derivative of the inside function, chain rule. The derivative of inverse sine, 1 over square root 1 minus x squared. All right, so if we want to clean that up at all, it's going to give us a negative 1 over inverse sine squared square root 1 minus x squared. Not really any cleaner way to write that. That is about as good as we're going to get. All right. B. So in B, you know what, I am going to write this underneath over here. I think I might need more space. So here we go. In B, f prime is the first function, x, times the derivative of the second, well, the derivative of tan. Notice again, this is square root x. Tan is 1 over, or inverse tan, 1 over 1 plus square root x squared times the derivative of that square root of x, which is 1/2 x to the negative 1/2. So trying to make it difficult on us. In fact, I'll change those bigger parentheses to brackets here. And then, of course, we are adding, this is product rule, first function, second function. So this is the first function, derivative of the second, plus second function, inverse tan square root x, times the derivative of the first. Well, the derivative of the first is just 1, since it's x. All right? So I can try to clean this up just a bit. I'm not going to go too far into it. Notice, let's see here, this, here's what I'll do. I'm going to move that 2, I'm going to take this 1/2 and move this 2 into the denominator. Notice that this thing squared is just going to be x, right? Square root of x squared is x, but this 2 is going to come into the denominator, and I could multiply it if I wanted to. But then I'm going to say that this x times this x to the negative 1/2, since they're both in the numerator where they sit, when I multiply those and I add the powers, I get x to the positive 1/2, or what is square root x. So this becomes square root x in the top over, I won't multiply this out. I'm going to say 2 times 1 plus x in the bottom. That's just some algebra. Plus, this one doesn't change. It's just inverse tan square root x. All right? I think that's about as easy as we need to make this. I'm pretty sure that my math lab question would accept something like that. I'm sorry, WebAssign, not my math lab. All right, there we go. Slightly more complicated again. This one was a chain rule problem, and then this one was a product rule problem. Let's roll on. We're almost done. All right. A derivative that can be simplified. And this one's pretty nifty in the way this one works out here. So let's roll right in. We are asked to take the derivative. Well, it doesn't really say, but the directions here indicate that we should take a derivative. So before I do that, actually, I don't like this arc sign way of writing it. So I'm going to rewrite it. Inverse sine of x plus, and then I'm going to take this other one and I'm going to say it's 1 minus x squared to the 1/2 power. Now that is what I'm going to differentiate, all right? So y prime, now, again, I'm differentiating this version. Y prime equals, well, derivative inverse sine is 1 over square root 1 minus x squared. Notice that the input was just x, so no changes. This is just straight application of the formula. And then plus, I'm going to have to use the product rule here. So plus first function x, second function 1 minus x squared to the 1/2, which has a chain rule in. So plus first function times the derivative of the second. Derivative of the second is going to be 1/2, 1 minus x squared to the negative 1/2 times the derivative of the 1 minus x squared, which is negative 2x. All right, plus second function, 1 minus x squared to the 1/2 times derivative of the first. Derivative of the first is 1. Whew, getting pretty lengthy there. All right. Now, the way it looks, it's ugly. But this one actually cleans up fairly well. I will remind you that if this was an AP free response question, it wouldn't be. But if it was, you would not have to clean this up. If it was a multiple choice question, I guarantee you this is not one of the options in the multiple choice. It's just not. You're going to have only the simplified version as an option. So you do need to know the algebra of simplifying this. So let's play around with it just a little bit here. I'm not doing anything with the first one just yet. I'm going to leave this 1 minus x squared on the bottom. And over here, this is where the real work comes in, right? Notice that this has a negative exponent. It's going to move to a denominator. Notice that this 2 can cancel off that 2. And I've got an x here and an x here with a minus that are all in a numerator. All right, so I don't necessarily need these brackets, by the way. So this becomes x squared over positive square root 1 minus x squared. All right, that's this piece here. And then this is just a square root, so plus square root 1 minus x squared. All right, that looks much better, right? Not bad. And notice that the denominator here matches the denominator here, so we're almost able to put these together. In fact, if I just took this and let's say this is technically over 1, and I multiply it by a common denominator, square root 1 minus x squared over square root 1 minus x squared, then this starts to clean up. I've got the same denominator in each piece, here, here, and technically here. And so it's 1 plus x squared plus, well, the product of square root 1 minus x squared times square root 1 minus x squared is 1 minus x squared. All over that denominator, square root 1 minus x squared. So if I go a little further, 1 plus 1 is 2. The x squareds cancel. Did I make a mistake? Did I miss something? Yes, I did. Yes, I did. Yes, I did. It's a good thing I have a key. You guys might have picked up on it. I dropped this negative right here. That negative disappeared on me. It should have been here. So let me put it back. All right, this negative right here I missed. So correct yourself there. And that means that, whoops, that means that this should be, whoops, that means that this should be a minus right here. So that negative is that negative. All right, now 2 minus 2x squared all over square root 1 minus x squared. And there is one, you may not see this right off the bat. That looks pretty clean the way it is, but there is one more simplification we can do. If you factor 2 off the top, notice we've got 1 minus x squared technically to the 1 power, right? And the denominator is 1 minus x squared to the half power. So if you divide like bases, right, base here and the base here are the same. This is to the 1 power, this is to the 1/2 power. You subtract exponents, you can actually cancel the square root off the bottom if you write this as 2 square root 1 minus x squared. All right? This and this cancel off and leave you with, I should say, the 1 there cancels and leaves you with a half when you cancel that bottom one. All right? Hopefully that makes sense, because now we've got a nice, neat, simple answer to square root 1 minus x squared. Whew. Boy, that problem simplified pretty neatly. Now, the whole reason for doing that and simplifying is to recognize this part here. From example 5, you can see one of the benefits of inverse trig functions is that they can be used to integrate common algebraic functions. What is so common? Square root 1 minus x squared is a circle, right? Algebraic function x squared plus y squared equals 1. It's the unit circle. And what we've just done is we have shown that the integral of this, the integral of, if you were to solve this for y, right, the integral of the top half of that circle, basically, is 1/2 all this mess. All right, why is it 1/2? Well, because we just showed that the derivative of all this was 2 square root 1 minus x squared, and our function is missing the 2. And so therefore, that 1/2. Now, we're throwing an integral into these notes, but the integration of this stuff is not going to show up until the next section tomorrow, so I'm not going to worry too much about that. All right, real quick here, there's a discussion very briefly on what we call elementary functions. I'm going to let you read this on your own so I can cut these notes off in just a moment. I just want to point out, again, I would take a moment and read this. It's a nice little review, or I'm sorry, a nice little history lesson on this. but also talks a little bit about Galileo, but also the most important piece, the reason why I put it on here is that it talks about what we call elementary function. An elementary function is a function from the following list. All right, it's a function from this list below, and the sum, product, quotient, or composition of any of these functions technically fall into the category of what we call elementary functions. Most of the most difficult functions and scenarios we can think of can be modeled with algebraic functions, with elementary functions. And these polynomial, rational, and radical functions, along with logs, exponential, trig, and inverse trig, all fall into the, quote, elementary functions. BC calculus goes into the process of representing non-elementary functions in terms of elementary functions. All right? And then finally, the last page here, which I will pull up in front of you and then pause, or then tell you to pause the screen. The last page just reviews all of the trig rules that we have, all of the differentiation rules that we have learned so far. This is a review of all of our differentiation rules. In fact, there won't be any more. This is it. All right, notice I crossed off the inverse secant, inverse cosine, inverse cotan, inverse cosecant, because those are not functions that we deal with often. You won't see them on the AP exam, even if the AP exam had their full original format. But here you are, and I circled the two that we dealt with today, inverse sine, inverse tan. All the rest, 1 through 18, you have learned up to this point already in previous lessons, and you have practiced plenty. So these are the basic differentiation rules for our elementary functions. These technically 20 rules are the rules that you will live by in this course and going forward with any calculus class you take from here. All right, that concludes these notes. Ask questions in class if you got it. Hopefully you got a good lesson out of this. Hopefully you'll learn quite a bit. Thanks.